Good morning, all. Myself Ramya, Assistant Professor, Department of EC, working in Hindustan College of Engineering and Technology. I'm here to discuss about image enhancement by spatial filtering under the heading of digital image processing. So, image enhancement helps to enhance the image such that the image is made better for visual perception. So for that, one technique involved is spatial filtering. Spatial filtering is the term which helps to perform filter operations on an image. The filter operation is performed by means of moving a filter mask from point to point along the pixels of the image. So this is an image enhancement algorithm, and this filtering technique is applied directly on the pixels of an image. So it is called as spatial filtering. The filter term which you are using for analysis is called as subimage. It can also be called as mask, kernel, template or window. The values which are available in the filter subimage are referred to as coefficients. So the mechanics involved in spatial filtering is that we have to simply move the filter mask from point to point in an image. At each and every point of x comma y, the response is calculated based upon the predefined relationship, and that value will be replaced with the center pixel. So this spatial filter can be categorized into two. One is smoothing spatial filter, another one is sharpening spatial filter. Smoothing spatial filter helps to blur the image such that the noise is reduced. This smoothing spatial filter can be of two categories, which is linear filter and non-linear filter. Non-linear filter can also be called as order statistics filter. To start with, first linear spatial filtering. In that, first the image is taken. The pixel which you are going to find the response is considered as f of x comma y, and the above row is x minus 1 row, below row is x plus 1 row, and this column is y minus 1 column, and this column is y plus 1 column. Accordingly, the coefficients are named off, and similarly, the mask coefficients also represented accordingly. W of 0 comma 0, 0 comma 1, 0 comma minus 1. Above is minus 1 comma 0, minus 1 comma 1, minus 1 comma minus 1. So the first step is that we have to place the mask over the image, and in that region each and every weighted coefficient and the respective pixel has to be multiplied together in the corped region, and all the products are summed up so as to get the response as a sum of product form. After getting this sum of product form, that response has to be replaced with the value which is available here as f of x comma y. This is called as spatial filtering, particularly linear spatial filtering. Linear spatial filtering involves sum of products. Likewise, after performing and finding the response here, you have to slide the mask to the next pixel, making this as f of x comma y, and the response is calculated, and replace this pixel with the response value. Likewise, the mask is slided over the entire image pixels, and the response is calculated, and the image is smoothened. In general, the expression is given by g of x comma y is equal to, this is convolution operation, weighted coefficient, and this value, the pixel value is made a product, and all those things are summed up. And particularly if you go for that is masking process, and if you are going for smoothing linear filter, particularly averaging filter, the averaging filter performs the sum of product, and that will be divided by the value of the number of pixels which are available, which is actually, so for example, if 3 by 3 mask is considered, so this is 3 by 3 standard average mask, where the weights of the weights are represented as 1, 1, 1. So if you carve this mask over the image, we will get the output, and that has to be divided by 9, because 9 number of pixels are there. That gives you the average. If you want to give weighted average, the center pixel can be provided with a more value of 4. And if suppose this is the mask provided, which is 5 by 5 mask, so 25 pixels are there. So to get the average, you have to divide it by 25. So this is the original image, and these are the masks which are used to smoothen this image. The order of the filter is varied from 3 by 3, 5 by 5, 7 by 7, and when you increase the order from the image, it is well clear that image is getting more smoothened when the order of the filter is increased. The next category is nonlinear spatial filtering. Here, the sum of product form is not included. Instead, ranking is incorporated. For that, the best used filter is median filter. And what we are going to do here is that, for example, consider this is the image, and the median filter which is used is 3 by 3 means we have to corp that respective region, and after corping that region, the pixels which are corped under that will be sorted out in ascending order. So that 10, 15, 20, 20, 20, 20, 20, 25, 100, and after sorting out, the median value is taken. Median value is the mid value. So 9 pixels are there. So mid value is 5. So fifth pixel value is 20. So you have to replace that. You have to replace this 100 by 20. So if you replace this 100 by 20, we can able to smoothen the image in a better form. Instead of 20 to 100 abrupt transition, now 20 to 20 smoothening is performed. So this is the original image where the noise are there, black and white, black dots are there, and that has been removed by median filter. So median filter is better in removing salt and pepper noise. And the next one is sharpening spatial filter, where the image is sharpened, edges are sharpened. Previous case is averaging, which is like integration, whereas sharpening is like differentiation. So to sharpen the image, we have to undergo two forms of derivative, first derivative and second derivative. When you apply first derivative on an image, we find that it is 0 under flat segment, and it is non-zero at the onset of gray level, and it is non-zero along ramp. So first derivative is the difference between the current pixel and the immediate pixel. Second derivative is the consideration of current pixel and previous pixel and the next pixel. And here when you observe the property, it is 0 in flat areas but non-zero at the onset and end, but 0 along the ramp. This is the difference between the first derivative and the second derivative. Whereas this second derivative provides more sharpened detail because it provides only non-zero value at the onset and end only, not along the edge. Only during the start of the edge and the end of the edge you will get the non-zero value, so which provides the edges very clearly. And the most preferable second order derivative is Laplacian operator, which is actually derived by Rosenfeld and Krag, and it is the simplest isotropic derivative operator, which is given by dou square f by dou x square plus dou square f by dou y square. And along dou square f by dou x square, if you consider previous and successive pixel, you will get this expression, and dou square f by dou y square, you will get this expression. So Laplacian is del square f is equal to this plus 2. If you add this, all the values will be, that is adjacent neighbors will be having 1 and the center pixel will be minus 4. So the mask is minus 4 here, remaining 1. If you consider all directions 1 and here minus 8. Instead of minus 4 here, you can introduce 4 here and the neighbors to be minus 1. So when you apply Laplacian operator, this is the original image, this is the Laplacian mask. When you apply this over the original image, what will happen is you can sharpen the edges very clearly. So Laplacian filter helps to sharpen the image, edges will be highlighted more. And so as a summary, in this lecture, we have seen about spatial filtering, which helps to enhance the image and to make the image better for visual perception. For that, two categories are used: smoothing spatial filter and sharpening spatial filter. Smoothing spatial filter tries to smoothen the image by means of removing the noise. Under that, we have seen linear filter and non-linear filter. Linear filter, we have seen about average filter, mean filter, and non-linear, we have seen about median filter. And next one is sharpening filter. Under sharpening, we find that second derivative finds a better output. So that under second derivative, most commonly used second derivative operator is discussed, which is Laplacian operator. And these are the references which have been referred for discussing this heading. Thank you. Thank you all.